Hi, everyone. Thanks so much for joining us for today's webinar, Model Convergence and Optimizing Runtimes with HydroGeoSphere. My name is Brayden McNeill. I'm the Technical Sales and Marketing Lead here at Aquanti, and I'm sorry that I wasn't able to attend the webinar today live. So this is actually a recording. But fortunately, there are plenty of my colleagues on the line today. So if you have questions towards the end of the webinar, we'll definitely have a chance for everyone to basically submit those questions, and some of my colleagues will be able to answer them. Before I get started in the webinar properly, I'd like to just make a short land acknowledgement claim. Aquanti is based in Waterloo, Ontario, which, as you can see from the image on the right, is located right in the middle of what's known as the Haldeman Tract. This tract of land extends 6 miles on either side of the Grand River from its headwaters all the way down to its outlet in Lake Erie. And this land was actually granted to the Six Nations of the Grand River as compensation for their role in the American Revolutionary War, the War for Independence. Unfortunately, as you can see today, less than 5% of this land within the Haldeman Tract is currently under the administration of the First Nations, the Six Nations of the Grand River. We wanted to just make this short land acknowledgement to acknowledge the fact that we at Aquanti are very privileged and happy to be able to live and work in the Waterloo region on this native land. Okay, so let's jump into the webinar. So for any new or long-term existing HydroGeoSphere users, you'll understand that HydroGeoSphere is a fully integrated hydrologic model that contains a wide variety of different governing equations of flow, many of which are nonlinear. HydroGeoSphere couples all of these different governing equations tightly into a single global matrix, which is then solved simultaneously. So as a result, if we were to compare HydroGeoSphere to similar models, whether they be groundwater only or surface water only models, in comparison, HGS models are very complex and they do tend to take a very long time to run and converge on a solution. We have many users who struggle with achieving convergence in their models, or once convergence is achieved, simply struggling with very long model runtimes. And so we wanted to basically deliver this webinar and provide some basic guidance on best practices and tips and tricks on modeling with HydroGeoSphere to hopefully help you all to build better models that run faster and which therefore you can make more and better use of. So the webinar today is going to be split into two main sections. The first part of the webinar will be delivered by me, Brayden McNeill. I'll be talking about model convergence and how to build a strong conceptual model and essentially a very broad overview of the modeling process and the approach that you should take to be most successful when building these HydroGeoSphere models. I'll also try and include a number of basic tips and tricks and highlight key commands that users can use to improve their experience. In the second half of the webinar today, Dr. Killian Miller will be talking about optimizing the numerical solvers and commands and approaches to optimizing the numerical side of actually solving HydroGeoSphere models to try and squeeze every bit of performance that we can out of every model. So before you even start building a HydroGeoSphere model or really any numerical model, the best thing that you can really do is sit long and hard and think about some of these key questions. You want to think first about, you want to really understand what questions you're trying to answer with your model. And that's going to lead into the following questions, kind of considering what processes, governing equations, or domains will be represented in the model. Just as a side note, whenever I speak of a model domain, what I really mean is the collection of nodes that are all solving for a single set of governing equations. So the porous medium domain is solving Manning's equation. In the overland flow domain, we're solving the 2D diffusive wave approximation of the Sampanow equation, for example. So by understanding the question that your model is trying to answer, it will help you determine what kind of processes, governing equations, and domains need to be represented in the model. With that understanding, you'll then start thinking about what kind of data that you need to parameterize each domain or each set of governing equations. And finally, you want to really consider how water will flow into and out of your model. So conceptualizing boundary conditions for your model. In every case, we want to make our ultimate goal physical realism. The more realistic you can represent the real world in a numerical context, the easier it will be for your model to converge on a solution. So let's focus on these first two questions to get us started. First of all, if we think about what question I'm trying to answer with my model, or what the purpose of the model really is, it's going to help us to understand at a basic level where our mesh needs to be discretized. So if we're quantifying groundwater base flow to a stream, then we're going to want to discretize our model more accurately around those streams. If we're looking at drawdown scenario analysis for water supply wells, then we need to refine the mesh around those pumping wells. If we're looking at forecasting stream flow or flood forecasting based on design storms, then again, we're going to need to build in those streams as accurately as possible, as well as a accurate topographic representation of the overland flow domain. Same thing with contaminant transport and well capture zones. We're going to want to have higher levels of refinement in the area where those solute transport plumes are likely to move through. So every application of the HydroGeoSphere model is going to dictate the need for mesh refinement in different areas. If we look at this image on the right, if we had some pumping wells nestled right here in the middle of the model, if we were to use a local grid refinement approach, which is common in ModFlow, for example, well, the end result is that we're going to have all sorts of refinement that extends out to the edges of the model domain. And so these areas that I've circled, these basically are areas where we have lots of extra nodes, even though they're not in an area of interest, again, which is centered around these interior pumping wells. So in general, I think we can safely say that you want to only refine meshes, your model mesh, in areas of interest. It's going to help you to reduce your overall node count and your overall model runtime. And the best way to do that is using a triangular element mesh. So this is the first thing that we're going to recommend for pretty much every model. If you're using HydroGeoSphere, you definitely want to reduce node count as much as possible. And the very best way to do that right off the bat is by using a triangular element mesh. For example, this red outlined area might be a stream, might be a river network. If we're looking to model base flow to those streams, then yes, we're going to want to refine the model around those stream networks with less refinement, fewer triangular elements, and fewer model nodes in these areas further away from the streams. Next, we want to think about what processes and governing equations will be represented in the model, because in every case, if you add more governing equations, more domains, more processes that need to be solved, that means there are more nodes, more exchange terms, and more governing equations, more unknowns in your model. It's going to lead to longer runtimes. So at every turn, wherever you possibly can, you want to think about ways to reduce the overall complexity of your model while also maintaining a suitable level of complexity, or a suitable conceptual model that will still answer the questions that you need to answer. So if you're working on a deep geologic repository, for example, that's kilometers below the water table, then maybe it's not really necessary to run a fully unsaturated flow model. Instead, maybe you can run the model in saturated mode, which is a linear equation. It's going to be a lot faster and easier to solve. If you're interested in quantifying evapotranspiration, well, then that's an entirely new set of governing equations in and of itself. If we want to accurately represent ET dynamics near the surface of the soil, then we're going to need to make sure that we have sufficient layering near the surface, but maybe we can decrease the numbers of layers deeper in the model. If we're running a contaminant transport model, maybe we can use a defined flow field. This is something we'll talk about a little bit later on, but essentially it means the flow solution is predetermined, and we simply overlay the solute transport solution on top of that defined flow field. Or also, if you're running contaminant transport, maybe you just use particle tracking first, right? You don't need to run a full solute transport for every iteration of the model. There are cheaper ways of understanding a contaminant transport system using, for example, particle tracking. If we're focused on winter processes and snowmelt, well, that's something that we have built into HydroGeoSphere, but it actually takes quite a long time to compute. It might be faster and smarter to just compute those snowmelt fluxes offline and then apply them as a boundary condition to the HydroGeoSphere model, as opposed to having HGS do all the heavy lifting of calculating snow melt every time step. And sometimes you just have to recognize that the model is going to take a long time to run. For example, if you're running a density-dependent flow model, some of these earlier tricks like using a defined flow field, particle tracking, those aren't really going to work out for a density-dependent flow model. And in that case, good luck. You're going to have to think of other ways to try and simplify the computational load or reduce the computational load. So I guess that brings us back to, defining a very highly optimized model mesh, for example. Sometimes, though, we just have to recognize that model runtimes, they will take a considerable amount of time. Always keep in mind that the more complex your model is, the more number of nodes that are built in, it's going to definitely increase your model runtime considerably. Very weak rule of thumb is if you double your node count, it might quadruple your model runtimes. It's becoming more and more possible to model larger and more complex systems year by year, but you also have to consider that modeling is a very repetitive process. You're going to run scenarios. You might have to calibrate your model. You'll probably run your model dozens, if not hundreds of times. It's impossible to know before running the model how long it will actually take. And so as a basic rule of thumb, what you always want to do is err on the side of caution. You want to approach the modeling process with an austerity mindset. You want to treat the model as though, every little bit of complexity that you introduce, every additional node, is going to completely blow up your model runtimes, and therefore you want to find every bit of savings that you can find in the model, in model complexity, in the node count, et cetera, et cetera. So once you've kind of address those basic questions about what your model is meant to do and what kind of governing equations and processes are going to be built into it, it's going to help you understand as well what kind of parameters that need to be built into the model, which different material types and the parameters that go into the governing equations. And then we also want to talk a little bit about boundary conditions as well, because it's going to be impossible to converge on a model that has completely unrealistic boundary conditions. So conceptual models are going to incorporate all of the different parameters you want to do. You want to apply a physically realistic distribution of material types and parameters, associated parameters, and again, a realistic distribution of boundary conditions. So typically, in a regular HGS model, we're going to have overland flow. So we need to know land cover properties and distributions, and then variably saturated flow in the subsurface. So we need a detailed soil map or map of hydrostratigraphy. In the porous medium domain, that means being able to represent the different soil types and hydrostratigraphic units means you're going to want an accurate map of these different units, and then consider what kind of processes are going to be run to actually solve the model. If it's a saturated flow model, which is going to be a little bit easier compared to an unsaturated flow model where the parameterization is going to be a little bit more difficult and a little bit more complex. Saturated flow parameters include porosity, hydraulic conductivity, and specific storage. These need to be applied everywhere throughout your model domain, of course. And then in the unsaturated flow process, we're typically going to parameterize the Van Gunukten or Brooks-Corey functions. And so we need to have the associated properties or parameters for those functions for every soil type in our model domain. We can also potentially just use pressure versus saturation or saturation versus relative K tables instead of using the actual Van Gunukten or Brooks-Corey functions. A typical workflow is actually to use the functions to produce these tables. And so we'll sub those tables in instead of the functions themselves, because the tables will be a lot faster for HydroGeoSphere to process. So we'll have some more notes about that later on, and a key command that will help you to basically generate and use these tables. And when we're thinking about the flow processes in the subsurface and any other domain, we also want to have a mind on subgrid features. Are there fractures, macropores, or other hydraulic features in the subsurface that are going to provide preferential flow paths? If we do want to incorporate fractures, then we need to discretize the model domain around those fractures. Fractures will exist at the edges of elements. So the more detail that you build into the fracture mapping, that's going to really increase the number of nodes that you have in your model domain. So you might think about ways that you can get or sidestep the need to represent these features as discrete elements within the model. Could we use a dual domain approach or an equivalent porous medium? These are things that you need to think about before you jump right into numerical modeling. If you just straight up right off the bat say, well, we need to build in every single fracture in this entire model domain, then just be prepared for the fact that that's going to significantly, very likely will significantly increase node counts and increase runtimes. In the overland flow domain, we're going to need to know land use and crop type distribution. That's usually pretty easy to understand or to get access to that data, since it is on the surface of the Earth. We can easily access that data, but we also have to consider how those crop and land type distribution maps compare to our mesh resolution. Sometimes it'll be necessary to up or downscale property zone distribution maps for particular areas of the model domain where there is maybe higher or lower mesh resolution. The parameters that you'll need to include Manning's friction, which is directional, so X and Y friction coefficients. The evapotranspiration governing equations are based on Christensen and Jensen or Allen. So you'll want to take a close look at these references to understand all the parameters that go into the evapotranspiration governing equations. You'll typically need to apply root and evaporation depths and profiles. And again, here we want to think about vertical discretization. How many layers are going to intersect that root depth zone and that evaporation depth zone? Is there enough discretization in my layering to properly represent those processes? And there's plenty of other parameters as well to consider. The major thing here is to understand that if evapotranspiration is a very important process and something that you're interested in, you'll want to make sure that you discretize the layering in the subsurface just underneath the surface domain sufficiently. And again, we want to think about subgrid features, potholes, ponds, rills, and other small scale topographic features that will significantly impact surface flow. Is it necessary to represent each one of these types of features as a discrete element when we're defining the model mesh? Is it possible to represent these as subgrid features using something like obstruction and/or rill storage heights? This is something that we commonly do at Aquanti since we tend to work at very large watershed scales. It's simply not possible to resolve every single pothole and pond in the topography of the model itself. So these can be really helpful features for representing those subgrid features. Okay, we'll take a moment to talk about boundary conditions. So these are basically mathematical operations, mathematical operators that define how water comes into the model and how water leaves the model. If you work at the right scale in a fully integrated system, for example, at the watershed scale, the conceptualization of boundary conditions tends to become quite simple. Usually you can count on precipitation as being the only flow of water into the model, and then you would apply evapotranspiration and an overland flow critical depth boundary condition as the outlets. But depending on the scale of the study, and not only the spatial, but also the temporal scale, are other things like pumping wells relevant? If we're, looking at a 60,000 square kilometer catchment, local water supply wells probably are not going to factor into the overall model outputs all that much. If that's the specific focus of your study, then that might change, in which case you'll want to represent these pumping wells, for example. As you get into smaller scale models, the application of boundary conditions can get a little bit more complex. You might use precipitation, nodal flux, or specified heads as inflowing boundary conditions, specified heads in critical depths as outflows. There's really a huge variety of boundary conditions that you can use. I want to introduce you to the concept of constrained versus unconstrained boundary conditions. The classic type 2 boundary condition where you're specifying a flux, I like to kind of think of this as a constrained boundary condition. It's constrained in the fact that it's not able to modify itself based on the dynamics of the simulation at any given point in time. Other boundary conditions like specified heads will produce or put water into the model or remove water from the model, and will automatically sort of modulate the actual volumes of flow based on the flow condition itself. So I kind of think of these as unconstrained boundary conditions. Whatever the case is for your particular model, it's always important to keep a good eye on your water balance. We'll talk more about water balance a little bit later on, but you always want to think in realistic terms about how water is flowing into your model, how water is flowing out, and making sure that those boundary condition volumes and fluxes are at a realistic level. A couple of examples of very poor applications of boundary conditions. So boundary conditions are, as I said before, they're just mathematical or numerical representations or operators onto your matrix of equations that represent real physical phenomenon. But they're kind of dumb, right? They're just simply, they're again, just mathematical operators that don't have any idea of what physical reality looks like. And so if you're not careful, you can definitely produce really unrealistic and physically impossible situations if you apply boundary conditions inappropriately. So here a couple of sort of undesired or bad applications of boundary conditions to follow here. So our first example is applying a nodal flux or a pumping well boundary condition right next to a specified head boundary condition. So here we've got a bit of a drawdown cone as the solution, but maybe the real drawdown cone is much deeper and much more widespread. Well, why, in this case, why can't I reproduce the observed drawdown cone? Well, it's because you've actually placed the flux nodal boundary condition near a specified head boundary condition, which essentially is acting as an infinite water source, right? So if you're ever running a model like this where you're trying to recreate a drawdown cone, just be sure that the pumping well is sufficiently far away from any potential boundary condition interactions that will make it impossible, basically, for you to recreate that physical observed drawdown. Here's another example. What if we were to place a flux nodal boundary condition in the unsaturated zone? Well, this model essentially wouldn't be able to converge, and the reason is simple. It's because you're basically removing a specified volume of water from the model, but it's from a location where the water isn't actually there. So in this kind of situation, I think HGS would basically be unable to reach convergence, and your model would just essentially run and run and run ad infinitum. Yeah, it would never really reach a solution. What if we were to build a model where we have basically rain flowing into the model and we've got evapotranspiration leaving the model, but they're not perfectly balanced, and maybe the precipitation is greater than the actual evapotranspiration, and you forget to include an outlet for flow, for example, a critical depth boundary condition in the surface domain. Well, in this case, the model would likely converge, but if you were to let the model run over a long enough period, the water balance would be out of whack, and so what you would end up seeing is just an ever increasing water level, and you would basically be recreating sort of a biblical flooding condition. And this is actually sort of an example that we see kind of frequently if you're running a small site scale model, let's say of a particular stretch of a stream, and we're looking here at a cross section at the downstream side of the model. Maybe we've applied some critical depth boundary conditions on the surface so that we can see water, just whatever water accumulates in the stream channel itself, just flowing out of the model. But at the downstream side, maybe we've also applied a specified head uniformly across sort of the downstream cross section to represent regional groundwater levels. Well, if we're not careful, we might actually apply a specified head and a critical depth boundary condition on the same nodes. So what would end up happening in that situation? Well, you basically are placing an infinite water source, the specified head boundary condition, right next to a critical depth boundary condition, which is essentially an infinite outlet. It will continue to remove water ad infinitum, depending on how much water there is at that node. So what ends up happening here is your time steps will just get shorter and shorter and shorter. It's effectively making your model runtime so long that it would essentially just never converge on a total solution at the time, the simulation duration that you're aiming for, right? So here we've basically just created sort of an infinite feedback loop of water. The specified head would just keep feeding more and more and more water in. The critical depth boundary condition can just, siphon off all of the water that's coming in from that specified head without any constraints, right? So this would be a very unrealistic situation. So that's just, again, a couple of examples to illustrate poorly conceptualized boundary conditions. Boundary conditions, they are the way that model flows into and out of your model. So you need to kind of think about them in realistic terms and really understand how those boundary conditions work numerically. We've got a full theory manual. You got to read up on each of these boundary conditions and be confident that you're not creating a numerically sort of weird situation where your boundary conditions are going to interact in an unrealistic way. So now that you've kind of conceptualized your model, you've thought a lot about the different processes, the governing equations, the boundary conditions. So you've got a strong conceptual model. This is the foundation for building a good numerical model. But as you go into building the numerical model, again, you can take steps at every stage of the workflow to make the modeling process a little bit smoother and more efficient. So first of all, you always want to start slow and add complexity as you go. Start with a simple model, get it running, get it working, understand what's happening. And then once you've reached that understanding, then you start to introduce new things to the model. Don't go straight to a solute transport model with daily transient flow conditions. Try to maybe run just a flow model at first, using long-term climatic average conditions, for example. But even before you start to build the numerical model, one of the most important things is building a good, strong model mesh. So we'll talk a little bit about constructing the model mesh, a staged approach to your flow solution, and then adding new complexity to the model, and kind of using the staged approach to make your modeling workflow as efficient and as seamless as possible. So first of all, I'm not going to talk too much about building your model mesh. We actually have a webinar that we delivered last year. There's a recording on our YouTube channel all about that. How to build a highly optimized model mesh. But it is very, very much worth reiterating over and over that building a high quality model mesh should really be the foundation of every HydroGeoSphere model. Every minute that you put into building a higher quality mesh is likely going to save you many dozens of minutes further down the road as you go to run the model over and over. So there's two aspects that you really need to consider whenever you're building your mesh. First of all, you want to have fewer triangles and fewer nodes in the mesh. Of course, you always want to refine around areas of interest, but if you can cut out nodes in other areas of your model as much as possible, that's going to lead to lower HydroGeoSphere runtimes. The second thing to consider is the mesh quality. This is just a part of the finite element solution methodology and criteria, but in a perfect model, every single triangle within a triangular element mesh would be perfectly equilateral. As you move further and further away from equilateral triangles, you slowly start to introduce numerical instabilities, numerical issues that become harder to solve. So again, a better mesh quality is going to result in lower HydroGeoSphere model runtimes. So we've got a couple of I'll also just mention here, we always recommend using AlgoMesh to build HGS model meshes. This is the best commercially available application with the most advanced refinement and optimization algorithms. The images on the bottom left here show two examples of the same sort of project which have been run through different levels of quality optimization. On the left, we have a low quality mesh that has about 4,600 triangles, and that optimization algorithm ran in 3 seconds. On the right, we have a higher quality mesh that has almost 900 fewer triangles, and it took 5 minutes to run. So the mesh generation here took an extra 5 minutes, but you've saved yourself from actually having 900 extra triangles in the model mesh itself. And as you add additional layers into the 3D mesh, that could translate into, several thousands or tens of thousands of fewer nodes. And the fewer nodes that you have, you're going to, these 5 minutes that you spend running a higher quality optimization for your triangular element mesh, you will very likely save hours after the fact in model runtime. Okay. So this is really foundational. It's important to take your time and construct a very high quality mesh. I'll also just point out that if you're putting in a lot of polylines and polygons that aren't perfectly intersecting within your model mesh, you can generate these issues, this telescoping mesh. I think in these images, this is fine. This is actually by design because there are going to be pumping wells located at these nodes. But whenever you produce your triangular element mesh, definitely look throughout the mesh for any of these telescoping effects in areas where you don't expect them. You can very quickly, if you have a telescoping effect somewhere that you don't realize, can very quickly result in tens of thousands of additional triangles and nodes that you don't need or want in your model. So again, higher mesh quality, producing a very high quality triangular element mesh is foundational. It's extremely important. Don't shortchange yourself here. Another aspect of a conceptual model that we haven't really discussed yet is initial conditions. It's very critical, actually, part of the modeling process. Whenever you start to run a model, there needs to be an initial condition, or the starting point, the initial head value at every node throughout the model. You have to apply them to both the porous medium and the overland flow domains. The other domains will all pick up their initial head distribution based on these two PM and OLF domains. There's a couple of different ways that you can apply initial conditions. You can use a homogeneous value across the entire model. You can base your initial head based on the ground surface elevation. In other words, your model would be fully saturated. Or more commonly, you can use an initial head that's mapped out from an earlier model run. In the next couple of slides, I'm going to be using the term steady state and transient. I just want to quickly note that HGS simulations are very nonlinear, and they include flow processes at at different time scales. Overland flow is a lot faster and flashier than groundwater flow. And so therefore, we don't actually recommend running HydroGeoSphere in steady state mode pretty much ever. Whenever I say steady state, whenever we speak of steady state at a quantity, what we really are trying to say, it's steady state is not 100% accurate. It's a bit of a misnomer. What we really mean is a pseudo equilibrium solution where it's a long-term transient model run, but the application of boundary conditions are static, so they don't change over time. So when I say steady state, just in your heads, imagine me doing hand quotes. What I really mean is this pseudo equilibrium solution. So the best way to come up with an initial condition for model runs is to generally run your model until you produce a long-term pseudo-equilibrium, quote-unquote, steady-state solution, which can then be used as the initial condition for subsequent model runs. When you run this initial steady-state solution, doesn't really matter what your initial condition is. You can set it arbitrarily at whatever level you want. Over a long enough period of time, the overall flow field, the overall distribution of heads should trend towards the same value. It just might take longer in one situation for that pseudo equilibrium condition to be achieved. Whenever you run a transient model solution, and what I mean again by transient is essentially your boundary condition fluxes are changing over time, the initial condition becomes much, much more important because basically the frequency at which those boundary conditions actually change might make it so that the actual head distribution is going to be different if you change your initial condition, essentially. So in the image here on the left, right, we've got some boundary condition, maybe a pumping well turning on, turning off, etc. If we were to start with a higher initial head, then generally we could probably in hand wavy sort of idealized world say that, you know, if the initial head is higher, then the overall distribution of heads is going to be higher over the course of that model run, even if the boundary condition fluxes are the same from one model to the next. In other words, for a transient model run, it's very important to have a meaningful initial condition. So what we typically recommend people to do is to run a model using long-term climatic averages to produce a realistic distribution of heads across the model domain using this pseudo steady state, pseudo equilibrium condition. And then we would use the distribution of heads from this model run as the starting point for subsequent transient simulations that have time varying boundary conditions. Okay, so you've built up a very good model mesh. You've then built up your numerical model in 3 dimensions. You've applied your boundary conditions, et cetera, et cetera. What you're going to want to do is now you're going to start actually running the numerical models. And what we recommend here is to start very simple and then progressively add more complexity to the model. And I'll say that I kind of asked everyone internally the way that they would approach this. It's going to change from case to case. It might always look like this. But essentially, this is the type of workflow that you should look at running yourself. Start with a single domain, run this pseudo steady state simulation with an arbitrary initial condition, use the results from that to run then maybe long-term transient simulations using annual average data. And you can use the commands restart file for heads or initial head from output file, for example. And then once you've got that long-term, transient simulation figured out, then you can use that as the starting point to run more refined monthly or daily transient simulations. At that point, you might want to add a new domain. Or, as I said before, it might change the order here. You might start with a single domain, achieve pseudo steady state, then add in the OLF domain, run a pseudo steady state, then go on to transient. The lesson here is essentially just take things step by step, stage by stage. Being methodical is going to help you to troubleshoot your model and then pinpoint at what stage you start running into convergence issues. It's also going to really help you to understand your model. You'll produce a wide range of initial states that you can then build upon for subsequent simulations. And I should also note that every step within this is also going to be iterative. Killian will talk more about optimizing numerical runtime settings. And so at every stage here, you're going to also want to be tweaking the numerical settings as well. And then once we've finished the flow simulation, then we kind of take the same approach to running more complex problems, whether it's like a solute transport problem. Once we've got a good daily transient flow simulation, we want to move on to solute transport. Well, maybe we start with particle tracking before we actually run the solute transport model. And then maybe we'll introduce a single solute, but run it only in advection mode. And then once we've got a good solution there, then we can run it again using diffusion and reactions or dispersion. And at every stage, we can see how the results change. Again, this is going to help you to understand what makes your model tick. And it's going to help you to understand where issues crop up. If you just jump straight to adding every domain and every solute and every single reaction and process, and it doesn't run, then which of those things is causing the problems? You're going to have a hard time figuring that out. And then, as you go through the modeling process as well, it's extremely important that you understand how your model is behaving and then also challenge the results as well. Don't just take, far too often people will only validate their model results against real world observations. Maybe it's groundwater levels. If you're only looking at groundwater levels, you can definitely create some situations where you're perfectly recreating your water table distribution, but your model might still be completely unrealistic. So keep an eye on the water balance file. This is a very key file for understanding how water is flowing into and out of your model. The error percent is probably the easiest and most universally easy to understand metric for the water balance. Error percent, we generally want to aim for less than 0.1%. Less than 1% might be okay for earlier stages in the model. But at every stage, don't just look at water table distribution, for example. We also want to look at boundary condition fluxes, exchange fluxes between different model domains, changes in storage in each model domain, et cetera, et cetera. A very simple example. We've got 2 models here that have different fluxes in and out but the change in storage is the same, it's 0, and the percent error is also very small, let's say 0.1% in both cases. They have the same distribution of water tables. I would ask you which of these is correct. It really depends on the scale of the problem. In this case, we have 1 liter per second of water flowing in and out of the model. In this case, we have 1,000 cubic meters flowing in and out of the model. This one might be about right for a model that is representing a bathtub. This one might be about right for a small catchment. If we were to only look at the distribution of water tables, then we might say, well, both of these models are equally good. But by looking at storage, by looking at the fluxes of your boundary conditions, a different picture emerges. Okay, I want to just get into some basic tips and tricks and highlight some key commands that you can use at different stages here of the modeling process. While you're building your model mesh, if you're familiar with HGS, you know that you have to run grok, then PHGS, then HSplot, right? It's not necessary to go through 3 stages in order to produce some results at different stages of the modeling experience. While you're building your model mesh, there's a command called mesh detect plot, as well as report mesh quality, which you can apply these commands and run grok before assigning any parameter values, before boundary conditions, without applying any numerical runtime criteria. Essentially, these commands, you run grok, it's going to produce tecplot formatted output files that allow you to visualize the model without having to run it through PHGS. It's going to help you understand or confirm that your mesh looks the way it should, that you've applied all of your layers correctly, et cetera, et cetera. The report mesh quality command also will allow you to visualize potentially weak spots in your model mesh. So in this image on the right, the dark purples are triangles that are very close to equilateral, whereas these green triangles are kind of the low quality elements within this model. So these are going to be the weak points in your model. Once you've developed the mesh and you're happy with it, use the command read 3D grid. It makes it so that you don't have to reproduce the mesh every time that you run grok.exe. It will simply read a pre-existing mesh. So you can generate the mesh once and then just use this command for all subsequent times that you run grok.exe. Whenever you're applying new property zones or new domains, consider using all of these 2 tecplot commands. These also are going to produce results when you run grok. You don't have to run the full model. We've got K to tecplot, porosity to tecplot, overland to tecplot, fractures to tecplot. They allow you to visualize different aspects of the model without having to fully run PHGS. I mentioned earlier about the unsaturated flow functions versus tables. You can fully parameterize the Van Gunukten and Brooks-Corey functions, but if you nestle the use tabulated unsaturated functions command within the material definition in your mprops file, it will automatically translate those functions to the tabular values, which are computationally a lot faster. Quick note about evapotranspiration. We typically always recommend setting canopy storage parameter to 0. Unless you're running your model over very small times, the time steps of the model will generally be too large to effectively reproduce ET in the canopy. And so having a canopy storage parameter above 0 tends to just cause problems. So in most cases, we recommend setting that to 0. For boundary conditions, you should nestle tecplot output. Okay, within every boundary condition, it's just going to produce an output file that tracks boundary condition fluxes for that boundary condition on a node-by-node basis. Should really be a standard. And then I'll also just note that a lot of boundary conditions have optional constraints that you can apply to them to make them behave a little bit more intelligently. That example that we had before about a flux nodal boundary condition in an unsaturated zone. Well, you could apply nodal flux reduction by pressure head, which will automatically modify the flux value based on a user-defined pressure head. In this case, if it was completely dry, we would expect that nodal flux to reduce to 0. When it comes to initial conditions, I mentioned these commands a little bit earlier, but you can define the initial heads based on earlier model runs using restart file for heads or initial head from output file. Just carefully read how these work in the reference manual. Some of them work on all domains, some of them only work on the currently selected domain, et cetera, et cetera. But they both have their uses in different times. You can also produce a map of water table distribution, for example, in GIS, and then apply initial heads based on a raster file. And I'll just quickly note that in the surface domain, as you're running that early steady state quasi-equilibrium steady state model, you typically don't want to set the initial water depth in the surface domain to 0. Set it to something slightly above 0. It's just numerically easier to solve. There are also regional model commands. These allow you to map a lot of information from a larger regional model to a smaller sub-regional model that's nestled within the footprint of the regional model. So zone numbers, initial heads, as well as specified head, time varying specified heads, boundary conditions. It's a bit of an advanced workflow, but it can save you a lot of times if you're modeling in an area where there are some models available. So through the Canada One Water project, for example, we're basically slated to publish open source models for all of Canada. So these could really potentially save a lot of users a lot of time. And if you're running a flow simulation, I'll just just note here that you should always use the no nodal flow check command. Unless you're running a transport simulation, this nodal flow check, which is on by default, is not required. Using this command will save you a lot of time for your flow solutions. Once you do move to a transport simulation, consider defined flow. This will basically take a finalized flow solution, and it will basically overlay the transport simulation on top of this defined flow simulation. So you don't have to solve the flow solution every time you run your solute transport model. And then finally, we have these skip on, skip off, and skip rest commands. These are kind of quality of life commands that allow you to skip portions of the grok file. Very helpful while troubleshooting the model. You basically just choose a section of the grok file that you want to deactivate, and then you would put a skip on and skip off bracketed around that portion of the grok file. Okay, in summary, optimize your mesh as much as you really can. This is really, really, really central, very important. Whenever you can, you also want to simplify the complexity of your model. Reduce process complexity, and that's going to effectively reduce the number of unknowns in the model matrix. So, and again, this can really help in a staged approach. Don't go straight for a density-dependent flow model. Run your flow simulations first. Those will be a lot faster than the subsequent solute transport simulations. And start simple and then add that complexity as you go along. As much as you possibly can, aim for reality in your conceptual model. That applies to both boundary conditions, material properties, as well as initial conditions. And use every trick that you have in your sleeve to try and make the most out of every one of your models. All these time-saving tricks, they really add up. Even if they only save you a few minutes, due to the iterative nature of running models over and over, those minutes will, they add up. So that kind of brings me to the end of my portion of the presentation. So building a strong conceptual model and the general approach to modeling. I'm going to hand it over to Killian now, who's going to talk more about the numerical aspects of actually solving the system of equations and how you can squeeze every bit of performance out of that process. So over to you, Killian.
Okay, nice job, Brayden, and thank you for the handoff. Welcome, everyone. My name is Killian Miller. I'm the Senior Numerical Analyst at Aquanti. And for the second half of this talk, I'm going to be discussing model runtime optimization. I'll start off by describing the model discretization in HGS and how you can customize that. Then we'll move into solving the discrete equations over a single time step, and then discuss the time stepping that's available in HGS. And we'll conclude with a brief discussion of parallelization and restarting. So let's begin with the model discretization. So for simplicity, I'm just going to look at the variably saturated flow equations in porous media. And so that would be Richard's equation, which I'm sure that you're all familiar with. And for the rest of this talk, I'll be using the following variable definitions. Okay, so the equations are solved over an irregular mesh, which consists of elements and nodes. And in HGS, you can either have an 8-node block element or a 6-node triangular prism element, which are shown here. And as Brayden touched on in his portion of the talk, you should really take your time to build a high quality mesh. So a poor quality mesh may result in poor model performance, and by that I mean numerical instability or slower run times. And to help you out, we provide a mesh summary and mesh statistics, which are written to the echo file by Grok. So the mesh statistics focus on the 2D planar mesh, and they provide information on element area, the aspect ratio of the elements, which is essentially a measure of element quality, edge ratio, minimum angle, maximum angle, and then in the case of a triangular element mesh, also the distance to a right or nearness to a right triangle. And so it's a good idea whenever you're running HGS to always consult the mesh statistics to make sure that you have a good quality mesh before proceeding with your simulations. Okay, so in HGS we use a control volume finite element discretization. So we define a volume of influence or a control volume at each mesh node within our domain. And so the discrete equations mimic the governing mass balance equation locally over each control volume. And this approach is very importantly mass conservative. And we use standard linear finite element basis functions. So at the bottom left here, we have an image of what a control volume would look like at a node I. And then you can see the mathematical description of what the finite element basis functions look like. Okay, so here we have the discretized flow equations, and here we're showing a fully implicit discretization. So H is the total head, VI is the volume of the nodal control volume, delta T is the time step, A to I is the set of nodal connections to node I, lambda ij is the relative permeability evaluated at an interface between the control volumes, and gamma ij is the internodal conductance. And we'll touch on each of these as we proceed through the talk. Okay, so there's essentially two different approaches you can use to define your nodal connections. The default approach is using the full set of finite element connections. And so in that case, for block elements, the number of non-zeros in your Jacobian matrix is going to be bounded by 27 times n, where n is the number of nodes in your model. And for prism elements, it's given by the following equation. So you can see here that for the black node I, all the connections are given by the red nodes. Okay, so the other approach is to use a finite difference approximation. And in this case, we only keep the vertical and planar edge connections in the nodal connection set. And the effect of this is that it greatly reduces the number of non-zeros within your Jacobian matrix. So you can see for block elements, instead of 27n, you have 7n connections, so about 4 times fewer non-zeros. And for prism elements, you have about 3 times fewer non-zeros. And here you can see that the number of connections is greatly reduced. And so this can have a significant impact on the speed of your simulations simply because you have a less dense matrix and therefore you're doing less work at each time step. So it's important to keep this in mind, and we typically recommend that you run using finite difference mode. Okay, so flow time weighting. So if we look at the discrete flow term, which is shown here, then we can write the discrete equations in the following form. So here we're basically taking a kind of linear combination of those flow terms. And HGS allows you to choose this time weighting factor to be any value between 0 and 1. We recommend that you choose a flow time weighting of 1, which results in a fully implicit discretization, which is the default. Crank-Nicholson would correspond to 0.5, and then an explicit discretization, which we don't recommend due to potential stability issues, would result from taking the flow time weighting factor of 0. Okay, in HGS, you have the option of choosing how the relative permeability term is calculated. We recommend using the default setting, which is upstream weighting. This ensures monotonicity of the solution. For example, the saturation must belong then to the physical range 0, 1. You can also choose to use an upstream weighting factor as well as central weighting. So we mentioned the potential for having right triangles in your mesh, and that may cause 0 internodal conductances along some element edges. And the effect that can have is it can block the flow of water, which generates a reservoir, and this can lead to model instability and poor performance. In that case, we recommend using the command integrated finite difference for overland flow, which uses an in-center approach to calculate these conductance terms, and that will avoid these water accumulation issues. So there are two options for model coupling between the porous media domain and other domains, such as the overland flow domain in HGS. The first that we'll discuss is the common node approach. And in this case, matrix contributions from other domains are superimposed onto the porous media mesh nodes. So it has to assume a continuity of pressure head at the shared nodes. There's no need for direct evaluation of exchange fluxes, and the total number of unknowns is equal to the number of mesh nodes. The other option is to use the dual node approach. And in this case, there is an explicit exchange term between the domains which are coupled. There's no assumption of continuity of pressure head between the domains, and the total number of unknowns is the sum of the domain node counts. And we always recommend using the dual node formulation since it allows for explicit exchange between domains, and it also helps with convergence. Note that the total number of unknowns for the dual node count is larger than in the common node approach. So you're solving a larger system, which may take, which requires more work in the solution phase, which obviously affects model run times. Okay, so now we're going to move on to solving or how we solve the discrete equations in HGS. So for variably saturated flow in porous media, the discrete equations are nonlinear, and so we have to use an approach like Newton's method. Okay, so if we define the function f, then we're solving f of psi is equal to 0. And so here we show these are the basic steps of Newton's method. So at each iteration, we have to build a Jacobian matrix and define the Newton residual. We have to solve the linear system for the Newton step vector. If we're using a relaxation factor other than 1, then we have to update that. And then we can compute an updated solution and then check if we've satisfied our convergence criteria. So now I'm going to talk about each of these steps in more detail. So we'll start off with the Jacobian matrix construction. So the Jacobian matrix contains the derivatives of our Newton residual function f and the local connections in the set A to I implies that it's a sparse matrix. The sparsity structure is computed once at the start of the simulation. So that's the location of the non-zeros. And the partial derivatives within the Jacobian are approximated via a finite difference approximation. So in order to compute those derivatives, you need to define what the epsilon value is for that finite difference approximation, and that's done by the command Jacobian epsilon. And to ensure good stability in your simulation, you should make sure that you don't set epsilon too small. So a good rule of thumb that will minimize the error in the forward difference approximation is to choose epsilon as follows. And so I would typically recommend choosing a value of around 1 times 10 to the negative 6. Should be adequate for most models. During the Jacobian matrix construction, negative internodal conductances may result in internodal flow from lower to higher heads, and this can cause oscillatory behavior in Newton iterations. So we recommend using the command remove negative coefficients to set those to 0 during the matrix assembly, and that will typically improve the stability of your simulations. At each Newton step, we have to solve a linear system for the Newton step vector. And in HGS, we use a preconditioned Krylov subspace method, the default of which is biconjugate gradient stabilized. The convergence or the stopping criteria for this method are the maximum number of iterations and the residual tolerance. These can be set using the commands flow solver maximum iterations and flow solver convergence criteria. It's important to keep in mind that the Newton iteration performance depends heavily on the accuracy of the linear solve. A good rule of thumb to choose the residual tolerance is that it needs to be greater than root n times the machine epsilon. And the reason for that is due to the error in actually computing the residual itself. So it doesn't pay to choose it too small, and the default value of 1 times 10 to the negative 10 is typically a good choice for the residual tolerance. One of the features of the linear solver is that it has a built-in stall check. So if the residual does not decrease by a certain amount over a certain number of iterations, then the linear solver will be restarted. And this is useful for some difficult to solve problems. If the linear solver fails, then the Newton iteration itself fails, and then it has to be restarted. So it typically pays to restart the linear solver and not have to redo all of your Newton iterations over again. And you can customize the behavior of the stall checking using the commands range for stall, which sets the rstall tolerance, stall check parameter, which sets the window size, and number of stall cycles, which is the maximum number of solver restarts. And these are all set to good default values. In order to obtain fast convergence of the linear solver, the Jacobian linear system must be preconditioned. By default, HGS always applies a diagonal preconditioner. And then on top of that, it uses a level-based incomplete LU preconditioner, or ILUK, with a fill level K. The default is to use a fill level of 0, and it typically doesn't pay to set the fill level much higher than that. The reason for that is because as you increase the fill level, the preconditioner becomes more dense. And so when you're applying the preconditioner to the linear system, that requires more computational effort, which typically which may slow down the solve phase. The Newton update step optionally uses an under-relaxation factor when computing the updated iterate. Typically, you want to use a value of lambda equals 1, so you're using a full Newton step. However, it may be necessary to choose smaller steps to dampen oscillations, which can help improve convergence. HGS provides an adaptive procedure to set the relaxation factor lambda, which naturally approaches 1 as the iterate approaches the true solution. And this can be controlled via the commands compute under relaxation factor, compute under relaxation factor limit, and minimum relaxation factor allowed. And so here's an example of a case where you can clearly see oscillations in both del val and res val in the runtime output. And this would be an example where you would want to try modifying the under-relaxation factor. Okay, so there are two convergence tests that the Newton iterations use. So the first test is based on the size of the Newton step vector, and the second is based on the nonlinear residual. So the absolute tolerance controls the minimum distance between consecutive iterates, and that's controlled by the Newton absolute convergence criteria. And then the residual tolerance controls the maximum local mass balance error over the nodal control volumes. So typically, this would be the convergence criteria that you want to satisfy to ensure that you're achieving a small mass balance error. And the residual tolerance also controls or bounds the water balance error, which is shown by this equation here. So it's important to keep that in mind when you're choosing these tolerances. And of course, they're going to be model dependent. You have to decide basically what is a reasonable value for these tolerances. In addition to convergence tests, there are also a number of divergence tests for the Newton iterations, the maximum number of iterations, the maximum size of a residual at any step, the maximum change in the residual at any step, and then also the minimum relaxation factor size. And those various tolerances can be set by the commands shown below. Okay, so we've discussed how the discrete equations are solved in HGS, so now we can move on to the time stepping. So in HydroGeoSphere, we have a concept of output times, which is a subset of the target times, which is a subset of the time steps that our model goes through. With fixed time stepping, which is the default, you simply visit each target time in order. And so in that case, the time step size is controlled by setting the output times and the target times via the following commands. And this is generally not recommended because it may lead to solution stability if the time step size is too large. Instead, what we recommend is to use adaptive time stepping, where the time step size is determined dynamically based on a set of control variables. And so here is a little simple description of how the adaptive time stepping works. And you can see that it can be customized to a certain degree by setting the maximum and minimum time step multipliers, and also by setting the maximum and minimum time step sizes. So there, as I mentioned, there are a number of adaptive time stepping controls in HGS. There is a control based on the maximum pressure head over a time step, the maximum change in saturation, the maximum change in surface water depth, and the maximum number of Newton iterations. You must specify at least one of these controls in order for adaptive time stepping to be activated. So if you're using adaptive time stepping and a Newton solve fails, then the current time step is halved, and the Newton iterations start again at that reduced time. If you're using fixed time stepping and a Newton iteration or Newton solve fails, then the simulation also fails, which is another reason why we recommend using adaptive time stepping. And so here you can see an example of where the maximum number of Newton iterations was exceeded, and so the current time step was cut in half and the Newton iteration starts again. So at each time step, HGS provides the following runtime output, which is described in detail in Appendix C of the reference manual. There's a lot of useful information here, and it can seem a little bit daunting at first when you're looking at it, but it's actually extremely useful once you know what to look for. So of particular importance are the columns del val, which is the maximum absolute error of the current Newton iteration, and res val, which is the maximum absolute error in the, maximum residual error of the current Newton iteration. Below that is a summary of the adaptive time stepping, which shows the multiplier that was used for each of the, or that was computed for each of the control variables, and then the final time step multiplier that was actually selected by HGS. Okay, so now we're going to just briefly discuss parallelization and restarting in HGS. Okay, so the Jacobian matrix assembly and the linear solver are both parallelized. The linear solver uses a domain decomposition approach, which basically divides the model domain into a number of node blocks. And each node block is then assigned to a separate thread. Concurrency is managed by OpenMP. And so here you can see an example below, a simple 2D example of how a set of nodes are divided into blocks, and then what that looks like in terms of how the linear system itself is being solved. Okay, so some recommendations for running in parallel mode. First of all, we recommend that multi-threading should be considered only for sufficiently large models. It typically doesn't pay for smaller models, so you should always try running in serial first if possible. Parallelization is activated by setting the field number of CPU in the parallel index file, and so this has to be set prior to running HGS. The number of threads should be even and ideally a power of 2. And optimal parallel efficiency is typically around 100,000 nodes per CPU. So when you're choosing the number of threads, you should try to keep that in mind. Restarting an HGS from the last successful time step is enabled automatically. To restart an HGS simulation, you go into the parallel index file and you set the field simulation restart to any integer value greater than 1. And then you run HGS without running grok. If you need to update various settings in your model and run grok again, then we recommend starting a new simulation. By default, all existing output files are appended to when restarting. And restarting can be disabled by using the command restart right off. However, we don't recommend this. So finally, I'd like to wrap up with a few practical takeaways on the numerical settings. So for the flow solution, we recommend using the finite difference mode with the dual node formulation. Use fully implicit time weighting and upstream weighting of the relative permeabilities. And we recommend using the command remove negative coefficients. You want to take full Newton steps as much as possible. So we don't recommend using relaxation factor unless you observe oscillations in your Newton iterations. And if you do, then you can try using the command compute under relaxation factor. If that still doesn't help, then try specifying the under relaxation factor manually and decrease it slowly until convergence is achieved. We recommend always using adaptive time stepping to ensure stability of the solution. And in terms of your simulation and how fast it's progressing, you can always try to loosen the Newton convergence criteria if your model's having trouble getting past a certain point, and then you can tighten those up later. We didn't touch on transport solutions, but we also have some recommendations in the case that you are running flow and transport simulation. We recommend that you use the nodal flow check, which is useful for ensuring stability of the transport solution. Set transport time weighting equal to 1, so that's upstream fully implicit. We recommend using upstream weighting of velocities, And then in addition to the flow control variables for adaptive time stepping, there are also a number of transport control variables, for example, concentration control. All right, so like to thank you all for your attendance, and I'd like to open the floor now for any questions you might have.